And the first thing that we want to start with, or the first of the last part of section 1.1, deals with matching. So I'm going to do it a little bit backwards of what you sometimes see topics presented. I'm going to start off with the example, and then we're going to put the math attached to it. Okay? So this is an example dealing with matching, and it starts off as follows. It says, suppose we've got 5 people, and it was super duper lazy in terms of their names. Their names are A, B, C, and D. Feel free to actually put real names on these people. What will often happen is if you do see real people's names on examples, they'll often say something like a person's name that starts with A, your favorite person's name that starts with the letter A, ditto for B through E. Okay? And what we want is we also have 5 different jobs, and again, super not creative, just called them job 1, 2, 3, all the way to 5. Okay? That way it's really easy to write on the actual graph. So here's what we have. We know that these 5 people are qualified for some, but not all, of these 5 jobs. And maybe this is a question in an HR department or some such, or maybe the head of some department, and they need to get some people to actually take those 5 jobs, and they would really like to match up the 5 people with some jobs that are qualified, and not have something where, say, person B has no clue what's going on to job 2, but now he's got to figure it out. Yes, we all know that happens sometimes, but for this example, we're going to try not to do that. I shouldn't say try not to do that. We're not going to allow ourselves to do that. Okay? So here's how the people are qualified for the jobs. So here's how to read this particular graph. Person A is qualified to do job 3 and job 4. Notice the edge indicates the relationship between the person and the job. So if an edge exists, this means the person is qualified to do that job. Okay? So person B is only qualified to do job 3. Person C is qualified to do job 1, 2, and 5. Person D is qualified to do job 3 or job 4. And person E is qualified to do job 2 or job 5. Notice one of the things that's going on here, and this is actually a type of is a criteria of a type of graph. Or over here, these people, there's no edges between people because the edges represent simply the person is qualified for the job. So by not having an edge over here, that means your person is not qualified to be the other person. Notice how that doesn't even make sense. And then over here, we also don't have edges between vertices 1 through 5 because, again, job 1 is qualified to do job 2. Again, doesn't even make sense. So there's no edges. So in this case, you're only having edges between the left and the right side of the graph. Correct, but we're not going to have that definition yet. So I'm going to go ahead and label these guys. And just as a heads up, you can do matching in all sorts of graphs, but we're going to focus on this guy. And I went ahead and labeled this here. That way I can cover up the original stuff to the top, at the top that we already did. So here is our goal. Did I write it? I did not. All right. So the goal that we have, right, pen. We would like to find what's known as a one-to-one matching. In other words, we would like to match one person to one job. So between people and the jobs. Okay? Now, here's the fun part. If we want to try to match a person to a job, what we're going to do is we are actually going to, so strategy, or what we're actually going to do is we are going to select edges. Okay, so that's what we're doing here. So for example, if we want to start matching a person to a job, we could say that we're going to match person A to job 3, and then we would select this edge that's A to 3 right there. Okay? Now, let's do this strategically. If we're trying to find a one-to-one matching between our people and jobs, the underlying goal, or the not stated goal yet, so let me go ahead and actually state it, is if this is happening in some sort of business setting or wherever you have people in jobs setting, what would the person's goal actually be? Well, they'd want all the jobs filled. Well, you have 5 jobs and you have 5 people, so that would mean you would want to get one of these people in each of these jobs. So that would be the unstated goal that we have here. So let's go ahead and state it. We want to match all the people to all the jobs. Now, anybody have a guess on what some of the things are that we're forced to do? Anybody notice a person-job pair that we have to go ahead and select? Yeah, so if you notice over here, job 1, if we talk about this in terms of a graph, you've got here job 1 has degree 1, so we have to go ahead and match person C with job 1. So I'm going to go ahead and highlight the edges we used. You guys are also saying B3, yep, same reason. Person B is also degree 1, so we're going to have to go ahead and put person 1 in job 3. Now, once we do that, is there anything else that's forced? In other words, does that mean we have to do anything else? Ooh, somebody said 2 and E. Okay, so for job 2, yeah, job 2, only 2 people were qualified. C, who's already been assigned a job, and E, so that would mean 2 and E has to be forced. I actually saw a different one, not the one you guys said. Okay, so you guys said here 4 and D. Okay, so D is only qualified for job 3 or job 4, so D has to be assigned to job 4. And then, so it turns out there's not one unique matching. So yes, as a couple of you guys noticed, depending on where you started, you could do something different. So for example, you got, the first one that I saw that came in was people said to match D to 4. That's not the one I originally saw. I actually originally saw A and 4. So yes, you could actually go ahead and change these guys up and select this guy. But in either case, whether you picked A4 for your edge or D4 for your edge, what does that mean about job 5? Well, job 5 right here would say that, well, in terms of what we've currently highlighted, so I don't have to undo the highlighting, 5 and A is not qualified for job 5. So this might be a situation where the companies or the business or whoever was doing this says, you know what, I got 4 of the people, they're going to be assigned jobs that they can definitely do. Person A, sorry, but you have to do job 5. I know you're not qualified for it. Figure it out. Okay. Now, in terms of the matching, what does this mean for the matching? Okay. Conclusion. So what we've actually done right here is we found a matching, but it's not a matching that uses all of your vertices. Okay? So all this is called is a matching. Okay? Because what did we do? We matched vertices to corresponding vertices along their edges. Now, because we were forced to stop and we can't add an extra edge, this is actually what's known as a maximal matching. Please tell me that's the first one I wrote down. Excellent. So we're going to go over different types of matchings here for just a second. Yes, I know your book is very vague at this point, so I'm going to give you the actual details. So the thing called a maximal matching is it's a matching where you've gone ahead and matched your vertices in one sense in your graph to other vertices. And what happens there is you get to the point where you can't add any new edges. So for this guy, we put in all of these matches, we put in all of these edges. We cannot add any extra edges to our matching. So this guy is actually known as a maximal matching. Why? No more edges can be added. Okay. Now, turns out matchings are not unique, which means you have lots of different options. We pointed that out when we said we didn't have to do D4. We could have done A4. And one of you actually mentioned down here E. We didn't have to do E2. We could have done E and 5 down here. Yes, there are different ways that you can put in your matchings. So in this particular situation, what happens, depending on how you pick your edges, different matchings, you can also get it so that when you pick your different edges, you can find the matching that has the most possible edges for the particular graph. Now, if you have somebody that has the most possible number of edges in your particular graph, this one is called a maximum matching. Okay, notice the only difference between these two guys, and this is a thing that actually happens in math relatively frequently, is just the ending of that word. So difference is maximal, you can't add any extra edges. Maximums means you have the most edges possible in a matching. Please note, so let me put a comment over here to the side, all maximum matchings are also automatically maximal matchings. So there is a thing that can happen, and we'll look at an example here in just a second. There is a thing that can happen that you can have a maximal matching that's not maximum. In terms of your book, it's actually looking for a perfect match. So we haven't gotten to that one yet. So a perfect matching is where you actually have gotten all of the vertices to be included as endpoints of your edges. And this is one of the issues in section 1.1. Section 1.1 of your book surveys lots of different topics, and I actually threw in extra terminology for us than what your book actually covers as well. But one of the things he does do is he hand waves a little bit, and he hand waves extra lots in terms of matchings. Ooh, interesting question. So the question that came up is the difference that a graph will always have a maximal but not always a maximum matching? And the answer is no. It turns out you should always get both of them. So maximal is just you can't add the extra edge at some point, and maximum is you take all your maximal matchings. So let me pull it down so you can see it. You take all of your maximal matchings, count up the number of edges in each of them, and a maximum matching is one of them that has the most number of edges. Okay? So you should always be able to get these guys. And if you don't have the word maximal or maximum, it's just a matching. Maybe you only pulled one edge from your graph. Not useful, but it would still be a matching. Okay? Now, the thing that doesn't always occur is something called a perfect matching. I know there's multiple ways of talking about matchings. The perfect matching is it's a maximum matching. It's automatically a maximal matching because we've used up all of the vertices. Okay? So here's the relationship between these guys. We've got a perfect matching. Actually, let me do a Venn diagram. That might actually be easiest. Perfect matching. I'm going to leave off the word perfect, not perfect. Leave off the word matching for the rest of them. All perfect matchings are also maximum matchings. And all maximum matchings are also maximal. It's not mean to write that sideways. It just totally happened because of the circle that I drew first. Don't draw your circles first. Okay? There's not been a poll yet, okay, to answer that question. All right, so let's go back to our example that we just had. So the example that we just had right up here, I went ahead and ordered the vertices so that we had all the people on one side, all the jobs on the other side. We started off with the edges we were allowed to use. We found a matching. It used 4 edges, and it turned out we couldn't add an extra edge because there were no extra edges going between the only 2 vertices we haven't used. So this guy is actually a maximal matching. Now, it turns out if you wanted to try to shuffle these edges around, maybe you didn't pick some of the ones that we picked previously, could you actually ever get it to the stage where you use all 5 vertices over here matched to all 5 vertices over there? In other words, could we actually get to the point where we've assigned all of our people to jobs that they are qualified to do? And the answer in this case is, remember how we built this matching. We built this matching because we tried to get to the perfect matching. We didn't call it a perfect matching at the time, but we tried to get to a perfect matching where we used all of our people and all of our jobs. So we started with our degree 1 guys, so vertex 1 and vertex B. And after we did that, we looked at all the things that were left and we logically went through it. So no, we actually built not just a maximal matching, but we actually built a maximum matching. So even if you rearrange the edges that you picked in here, it turns out you could get a matching that has fewer than 4 edges, but you'll never get a matching that gets more than 4 edges. So this guy actually turns out to also be a maximum matching. And here's the key thing, but it turns out it's not. And actually, this graph doesn't have a perfect matching. And the hatch marks there just so I didn't have to write the word matching again. I'm assuming you want the definitions. So these guys right here, that should be the entirety of the definitions except for the bottom half of the Venn diagram. Okay. But that's the crash course in matchings. Your book doesn't actually specify the buzzwords perfect, maximal, or matching, but from context, it looks like what he's trying to get you to do is a perfect matching, and if a perfect matching doesn't exist, at least try to get through a maximal matching. Okay. So I've got one other example prepped up for us in terms of looking at an example where you can have a matching that is maximal but not maximum, which I think is going to answer the question that just came in. Oh, I guess I have 2 extra examples prepped up then. So suppose you have something like this. So let me go with this next example, and then we'll get the thing that we were just talking about. In this case here, suppose you again have the same situation that we had in our first example, but it's a little different. Now you've got still 5 people, and you have 3 jobs, and you'd like to assign these 5 people to their jobs. Without putting in the edges, because I'm too lazy to do that, although we totally could, what do you guys think? Is there any possible way that a perfect matching could exist? So the question here is, can a perfect matching exist? And that's without even looking at the edges. Correct. And it turns out the answer is no here, and that is because the number of people, so A, B, C, D, and E, does not equal the number of jobs. It turns out if you want a perfect matching, you are going to actually have to have same number of people, same number of jobs if you divided your vertices into people and jobs. But in general, the only way you'll be able to have a perfect matching exist, and this doesn't guarantee it exists, it just says it's the potential for existing, is you have to have an even number of vertices. That way you can actually divide it up into 2 cases with your vertices. And it doesn't matter what edges are in there. But you can still get a maximal matching and maximal matching. That's fine. Just a perfect matching doesn't exist. Oh, excellent. Now I actually have the example I was thinking of before. All right. So suppose you have this little guy, and I've actually got the matching prepped up for us. So suppose you have the graph that has these 5 vertices, A through E, in that sort of weird shape that it is. The matching here is the one that's the edge right here, A to E. So this guy here that was attempting to be highlighted in orange. So what do you guys think? First of all, is it a matching? Yep, just the fact that you selected an edge. And here's the key thing with a matching. When you select your edge, especially if the graph is drawn like what you would think of sort of a normal graph all over the place, you're selecting edges that are not incident to each other. In other words, you're selecting edges that don't share the endpoints with anybody. So this guy totally is a matching. So let's write down what he is. So it is a matching. Now the next question is, in this matching, is it maximal? In other words, could we actually add in an extra edge here? We add an extra edge to the matching. And remember, when you add the extra edge, you can't reuse any of the vertices that are already endpoints of edges in the matching already. So right here, it is maximal but not maximum, yes. And let's do that matching. So this is maximal but not maximum. So if we grab this same graph, and it's going to look a little wobbly probably. Let's try to make it less wobbly. This guy, we have down here C, have E, and then we have D. What matching did you say? I'll actually pull your matching. AD and CE. Awesome. Yeah, so that then would be a matching that has more edges than the previous one. And we still can't add an extra edge to it, so this one is, again, a maximal matching. And it actually turns out to be a maximum matching because while there are some options that you can have here, for example, you don't have to use AD, you could have used AB right here. You can't get any more than 2 edges in this matching. So this example over here to the side, so on the right, is a maximum matching. And if you're a maximum matching, remember you're still maximal. So that would be the difference between maximum and maximal, where you can be a maximal matching, but not maximum matching. There is, I think it's a little bit later in your textbook, there's an interesting homework problem that I often give, and it's you're trying to find some matching, and people always get the maximal, but they forget to reorder it to get the 1 extra edge. So watch out if you're looking for the maximum number of edges possible. You sometimes have to reorder which edges you use. Notice here we had to stop using edge AE to get the maximum matching. Questions make sense? Kind of feeling okay-ish. All right, seeing no questions come in, the next little bit is some terminology. So what we want to define is we want to define something called a bipartite graph. And in fact, we've already used them today, and in fact, we used them previously as well. So bipartite graph is a regular old graph. It's got a vertex set, so B. It's got an edge set, E. But here's what makes it a bipartite graph. You can divide your edge sets, vertex set, you can divide your vertices into 2 groups. And we're going to call them group X and group Y. And here's the condition that makes it bipartite. All of your edges in the graph, so all the edges in the graph, are of the form where one of the endpoints of the edge is inside of the first set of vertices, and the other endpoint is in the second set of vertices. Okay? Note, in terms of an example, while we've already had one, our very, very first example where we had the 2 columns, totally a bipartite graph. So I'll do a baby example so we can see it right here. Or maybe you have something like this. This would also be a bipartite graph, very lazy bipartite graph. But I went ahead and put in the extra one so it didn't look like a sideways M. So that would be a bipartite graph. You can also have a bipartite graph that is not oriented in columns. It could actually be oriented very differently. So let me go ahead and label these guys A, B, C, D, and E. Maybe we actually throw those vertices in a different orientation. Maybe we have something like A, B, C, D, and we put E in the middle for whatever reason. So A to D, I'm just copying the same edges. Then we have B and D. Dig. We also have B and E. We also have C and D, and C and E. I definitely put the E in the wrong spot. Okay. So bipartite graphs don't have to be written in 2 columns or 2 rows, but that's their standard form, just because it makes life easier. Okay. Now, it turns out bipartite graphs are typically the ones you look at when you're dealing with matchings, but to do a little bit more on the theory side or the specific names of graphs, there's something called a complete bipartite graph. It does have an actual symbolic name. It's called K, capital K, and in the subscript it has 2 things, an N and an M. The N and the M indicate how many vertices you put in the 2 groups of vertices for your bipartite graph. Okay? So your the complete bipartite graph, your vertex set has two components, so your vertices are broken into two pieces. And the first piece or the second piece, it really doesn't matter. One of the pieces has n vertices and the other group has m vertices. The other condition is it is bipartite, so that does mean all of your edges have to go one endpoint in set x, one endpoint in set y, and here's the part that makes it complete. Complete means you put in as many edges as humanly possible. So let us look at an example, and let me write that down first. So, and there are as many edges as possible, where your edge spans the two sets. Now, let's actually look at an example. If we look at the example K23, and just as a heads up, K23 is actually the exact same graph as if you rearrange the order. It turns out it doesn't matter if you put the bigger number first or last in the subscript. By standard, most people put the smaller number first and the larger number second, but it doesn't matter. Okay. If you wanted to look at this guy, say maybe we looked at the two groups of vertices in terms of rows. So maybe you have something like this, put two guys in the top row and three vertices in the second row. So here, maybe we have A and B, and maybe in that second row, I'd do 1, 2, and 3, just so it's obvious which vertices are in which set. So notice here, in this top set, this would be our set of vertices that we'll call X. This guy would be our set of vertices that we call Y. Notice the number of vertices in set X is 2, and the number of vertices in set Y is 3, which matches those two subscripts. Note, in these complete graphs, if you want the total number of vertices, it's just going to be the sum of that subscript always. Okay? That's one way to check to make sure you haven't put in too many vertices. Now, if we want to go ahead and finish off this graph, we're going to put in as many edges as possible. So if we look at vertex A, he's only allowed to have an edge or be incident to an edge that has its other endpoint in the other set. Well, you got 3 possibilities for the other endpoint, so we're going to go ahead and draw in all 3 of those edges. Okay? So you could have edge A1, A2, A3, and in fact, in a complete graph, you have to have all of them. Same thing for vertex B. Any edge that has B as an endpoint, the other endpoint can only be in the other row. So that would be the other endpoint could be 1, 2, or 3, and in a complete bipartite graph, you're going to have all 3 of those edges in the graph. If you do not have a complete bipartite graph, if instead you just have a bipartite graph, if the bipartite graph has 2 vertices in one set of vertices and 2 vertices in the other group of vertices, you would have some number of edges less than these 6. You would have some subset of those 6 edges. Yes. So based off of what you guys were just asking in the chat, your total edge set here is going to be your cardinality of X times Y. Yeah. And that is because if you look at one of the rows, so say you look at this set X, notice the degree of each of these vertices is always going to be the same as the number of vertices in the other set. So the degree of A is the cardinality of Y, the degree of B is the cardinality of Y. So that gives you this part of the product and how many vertices we have in set X. So we add up all those degrees together to get the total number of edges. That's where the first factor of the product comes from. So that's a complete bipartite graph. And we use these guys all the time. Okay? But that's all there is for complete bipartite graph. Now, in many books, you actually talk about a complete graph before you talk about a complete bipartite graph. Your book actually doesn't even talk about a complete graph in this section, but you always put the two of them together. So let's talk about a complete graph, and then we'll get back to the things your book talks about in this section. So a complete graph has a very, very similar notation. It's actually one of the reasons a complete bipartite graph has the notation it has. It's got capital K, K for complete. I think it actually came from German originally. And the n here tells you how many vertices you have. So for this one, the number of vertices in a complete graph is going to be whatever that subscript n is. And the number of edges, well, the number of edges is as many possible edges as you could put on a graph with n vertices. So here, number of edges, as many as possible. But it's easiest to explain the complete graph if we actually look at some examples. So let me go ahead and we'll look at the first 5 complete graphs. Technically speaking, there is a K0. K0 is just, well, nothing. It's the empty set or the empty graph. You have no vertices, you have no edges. Okay. K1 has exactly 1 vertex. Any guesses how many edges it has? Don't overthink this one. We're simple graphs. Yep, no edges whatsoever. You guys totally nailed it. So I'm going to move on. So one of the things we'll do in the future is we'll look for subgraphs of whatever graph we actually have, and we'll say, hey, are any of our subgraphs also complete graphs? Well, everybody has points, so you're always going to have subgraphs of K1, and you almost always have edges, and it turns out K2 is where you have 2 vertices and 1 edge. So these guys here, sometimes people don't even bother looking at them because K1 is really just the same as saying, oh, I have a vertex, or there's 1 vertex. And K2 is really when you have just 1 edge. Now for K3, K3 is where you have 3 vertices. Any guesses here on what the graph might look like? Now remember, the graph has to have as many edges as humanly possible, and it's a simple graph. So what I've just drawn in with 1 edge is totally a graph on 3 vertices, and it's a perfectly fine graph on 3 vertices, but is it K3? Correct. It's not K3. K3 actually has to have 3 edges, so I'll go ahead and put in the extra 3 edges. K3 is actually relatively nice to draw. It totally looks like a triangle. Not going to lie, for the longest time, I just thought of K3 as a triangle. Not really geometry here whatsoever, but it definitely looks like one. Now, K4 has 4 vertices. You don't have to put the vertices in a triangular notation whatsoever, but it's standard for the complete graph to try to put your vertices roughly in a circle. The more vertices you have, the closer this thing looks like a circle. With 4 vertices, it looks like a square. And yeah, this guy will totally look like a square with an X in the middle, or how I normally describe it, it looks like a square with both the 2 diagonals. But either way is totally fine. It also looks like those little symbols you get on the internet when you try to click something and it's just like, no, you can't do this. Correct. So here, if you're looking for edges, so we can totally put the edge count in here. We have 4 vertices and 6 edges. We could do the same thing back with K3. Here we have, I did not mean to do an E, I'm just going to go with it, 3 edges and 3 vertices. Now for K5, and K5 is actually a special guy we'll see in the future. It's going to be a little ways in the future though. I'm going to go ahead and roughly put the 5 vertices in a sort of circular notation. If this was computer generated, I would actually try to get all of those guys equally spaced. But as it is, we're just going to go with it. Okay? So here, if we put in all the possible edges, I'll do it in a specific way. You do not have to do it in this specific way. Okay? I like to actually go ahead and put in the edges that go around the outside first, just because, yeah, there you go. I like that description. Just because I've dealt with geometry so much, and this now looks like a pentagon. All of the other edges are going to look like diagonals inside the pentagon, but you don't have to think about it that way in any way, shape, or form. So if we take this vertex at the top, what do you want to do? You want to connect that vertex with every other guy. So there's only 2 edges we haven't put in. Any other vertex, you look at it and make sure it's connected to all of the other vertices. Keep going around. Down here, you want to make sure that vertex, that one that's on the bottom right, is connected to all other vertices. It's almost there. We just need to put in one extra line. And as you check the last two vertices, it turns in all of the edges are there. And if you count up all of those guys, what you would come to is you would come to 10. Okay? And yes, there is totally a formula for the number of edges for a complete graph. It turns out there's a bunch of different ways to write it. Those of you who are typing it in there, you actually found a couple of them. The shorthand way of writing it is actually this guy. Where you have a grand total of, if you've done anything with combinatorics or statistics, you would know that symbol. If not, what that actually means is it says you have n objects, so n vertices, and you pick two of them. Yes, it is n choose 2. And that's actually where you got these numbers will come from. This is the same as 3 choose 2. This is the same as 4 choose 2. That's actually the same as 5 choose 2. If you don't know that notation of an n choose 2, don't worry about it. This is actually the formula right there. But it's up to you in terms of if you need that formula or not. The complete graph, just like the complete bipartite graph, is a graph that has the maximum number of edges on a particular number of vertices. So any graph that is on 5 vertices, so like this guy down here of K5, every graph with 5 vertices is a subgraph of K5. In other words, it's K5 where you've deleted some of the edges. So that's the big claim to fame with these complete graphs. Questions make sense, kind of feeling a little bit okay. All right, seeing no questions come in to you guys, we're now about to go into the next thing. So the next thing looks very different. And it is a definition. It's going to be dealing with something called an edge cover. Oh, I like that question. So the question that just came in, not going to go with edge cover, but the question came in is, can you have any number of vertices in a graph? And the answer to that is, it depends. If you're trying to build a graph of a specific type, you need to make sure you meet the criteria of that specific type. But in general, yes, you can build a graph with however many vertices you want. The number of vertices you have does have to be a non-negative integer. If you have 0 vertices, you literally have a blank nothing, an empty set if you tried to write it in terms of sets, or if you tried to draw it out, it would literally be nothing on the page. Okay? So typically, the number of vertices you have is 1, 2, 3, 4, etc. Some positive integers, normally what happens. Now, once you know how many vertices you have in your graph, that's when you start doing the stuff that we just did with both the complete graph and the complete bipartite graph. That's when you start looking at, all right, well, what edges do I need? Now, if your graphs were coming from some situation, your edges and your vertices would automatically follow from that situation. In other words, if you were modeling something out that was physical, you would physically have the thing that you were going to have a vertex represent, and you'd figure out how many of them you physically had. Right, so edge covers. So both edge covers and independent sets are highly, highly related, and we'll see what that relation is once we talk about independent sets. So first thing is an edge cover, and watch out, an edge cover is not a collection of edges. It is instead the set of vertices of your graph where every single edge in the graph is incident to one of the vertices in the edge cover. In other words, every single edge has one of its endpoints, or 2 if you needed it, but at least one of its endpoints in the edge cover. So every edge in the graph is incident to one of the vertices in the edge cover. That's the key thing. So let's see how this would work. And I went ahead and pulled an example, and I pulled this example from one of the graphs that's actually in your textbook. Okay? So what we're going to look at is we'll look at the situation where this graph models city streets. So the edges here would indicate some part, some street in your city, and each of the vertices here are going to model an intersection. So what the city planners wanted to do is they wanted to install street lamps to make sure everything was lit up. But they were cheapskates, or they just didn't have the budget to put in lights everywhere. Instead, what they decided to do is they were going to put lights only at the intersections. And they also, the other assumption we're going to assume here is notice how most of these little segments between intersections, these little edges right here, visibly look like they're the same length, but one of them looks longer. We're going to assume that if they put a lamp here at either intersection K or intersection J, so vertex K or J, that it'll be able to go ahead and light up this entire section. So it depends what you need. Technically speaking, when you grab your edge cover, you can totally grab every single vertex in your graph, and that would be a perfectly fine edge cover. But typically, we want to find the minimal edge cover, so the smallest number of vertices in the graph that will do the job. So the goal here is the smallest, but in terms of this definition is, you could totally just throw all of your vertices in and be just fine. All right, so our goal is going to actually try to find an edge cover that includes the smallest number of vertices possible. Okay, so in terms of the actual math, we are going to find a minimal edge cover. So that's the math terms. All right, so let's see how to do this. So in terms of scratch work, notice what we have. Okay, we have, well, how many vertices do we have in this graph? Anybody count that up? We'll go ahead and grab both the number of vertices and the number of edges. Yep, we've got 11. And we also, let's go ahead and find the number of edges. Anybody have a chance to count that up yet? Let's see. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This one does count as 1, and these lines here, they count as different ones between the breaks there. So we've got here 14 edges. Now, here's what we know for sure. I'm going to go ahead and walk us through the complete logical thinking process, even though a bunch of you have already put in potential answers. Okay? If we're trying to find an edge cover, remember, this is a subset, maybe it's the full set, but at least a subset of our set of vertices. So this tells us that the maximum number of lights that we will ever possibly get is going to be 11. So in terms of our edge cover, somewhere between 0, hint, it's not going to be 0, and 11 is going to be the number of vertices in our edge cover. And I definitely should have just scrolled instead of made that really tiny. Okay. So let's actually go ahead and start thinking about selecting those vertices. So if our goal here is to minimize, and let's actually put it next to the graph. So if our goal is to minimize the number of vertices we want to use, then, or needed, I suppose. I can't spell needed, that's terrible. Let us look at some things. Specifically, let's look at the degree of our vertices. If you look across all the vertices in this graph, there are a couple of different degrees in play. Anybody spot what the degrees are of these vertices? Yep, degree 2 and degree 3. So let's actually map out which vertex has degree 2 and which vertex has degree 3. I'm just going to list them out. So degree 2, guys, it looks like A is degree 2. Looks like D is degree 2. Let's see. It looks like both G and K are degree 2, and I is degree 2. So only the corner 4 guys plus G. So I'll put them alphabetically: A, D, G, I, and K. That was close-ish. Okay. Now everybody else is degree 3. So for degree 3, we have vertices B. We've got C. Don't do D, E, F, H, and J. Make sure I didn't miss any there. Now, so if we were looking to find vertices that would be key in saying we don't need to have as many vertices as in the entire graph, any guesses which category of vertices we would pick. Would we want to focus in on the degree 2 vertices, or would we want to focus in on the degree 3 vertices here? Yes, you definitely want to focus in on the degree 3 vertices. So if we look at these degree 3 vertices, we've got a grand total of 6 of them that we could play with. We also want to find an edge cover, and an edge cover means you want to make sure that all of your edges have at least one endpoint in your set of vertices that you choose. So we have 14 edges. That means we need to have at least 14 edges. That means we need to somehow get to 14 edges based off of these degrees. Okay? So if we look at 5 vertices that are degree 3, so this is number of vertices that I'm looking at, and this here is number of degree, or the degree of those vertices, this gets us to 15. Now, why would I have picked 3? Well, that was the degree, so we already said we wanted to focus on degree 3, guys. Why did I pick on 5? Well, because I was looking for some number that was at least as big as 14. 15 is a multiple of 3 that's the closest to 14, but not less than 14. Now, what does that tell us? That tells us that we're probably going to be looking at 5 vertices in our vertex set. Maybe we have all 5 of those vertices are degree 3 vertices. Maybe we have 4 degree 3 vertices and 1 degree 2 vertex. Okay? But this gives us an idea of how many vertices we might need. Now, depending on how the edges are connected, you may not actually be able to use 5 vertices, but we're definitely going to need at least 5 vertices. That being said, if we want to start looking for these vertices, any guesses on what might be a vertex to choose? That's all the scratch work, that's all the background stuff. Now let's actually find this edge cover, or a possible edge cover. Somebody said B. Okay, so if we want to go ahead and look at B, if we want the fewest vertices possible, that automatically means who should we not include in our edge cover? Yeah, don't include anybody adjacent to B. So we're going to cross off A, we're going to cross off C. I'm also going to go ahead and cross off F. Okay? That is degree 3, so that means there's 3 vertices that are adjacent to B. Now, you want an edge cover, so that means right now we only have 1, 2, 3 edges that are touching B. We need to still deal with some more vertices. So what would be another vertex that we should use? And let's do it systematically. So maybe go over here. Systematically, we would need to include somebody on the right side of the graph. Who would be somebody we'd need to include on the right side of the graph? Oh, you guys went the other way. I should have looked up. Oh, somebody answered me. I would not recommend going to H. Yeah, I would recommend, let's go ahead and include D right here. As soon as you include D, that says you don't need to worry about H. Okay? It does mean that you are going to also have to pick up G, though. Now, there is a problem with going to the right, and I think several of you may have spotted it when you said go pick up E. Anybody spot what the problem is when we went to the right? It's okay. Yeah, so we actually here, as a couple of you have said, we actually picked up 2 vertices that were both degree 2. So that actually means, oh no, we were trying to shoot for degree 3 vertices. We might actually not get a minimal edge cover when we go this way. So let's double check what we're doing, and we'll get all the way around and see if we can actually get an edge cover doing the strategy that we're doing. And if not, we'll come back and go the other direction. Yep. So here we've got D, we've got G, we've crossed off H. So if we keep going the same direction, who are we going to have to pick up as we go clockwise around this graph? The next vertex we're going to need to pick up is, right, we are going to need to pick up K, yep. And I'll go ahead and pick up E like you guys had said before. When you pick up E, you're not going to need to pick up I. And why would I have stopped going around clockwise after K? It all comes on that vertex J that we haven't done any markings on yet whatsoever. Yeah. In this orientation of the way that we traveled around the graph, because we picked up 2 vertices that were degree 2, we have to use vertex J right here. Just a second. we have to pick up vertex J. Now, count up how many vertices we just used right there. How many vertices did we highlight to put into our edge cover? Yeah. And what was our hypothesis at the beginning? How many edges did we think were going to be, not edges, how many vertices did we think would be in our edge cover or in our minimal edge cover? We were hypothesizing that we should only have 5. So what we just found is this is legitimately and totally fine as an edge cover, but it is not a minimal edge cover. It does turn out that you can totally get a minimal edge cover that has only 5 vertices. So let's go back to the graph up here and find the one that's actually a minimal edge cover. Now, question for you in terms of how I put this together. I can unhighlight all of the scratch work we had up here, or I can do a second color when we go back to the graph. Would you guys like me to get rid of all of these markings on the graph and start from scratch, or would you like me to use a second color? Okay. Careful, edge coverings or edge covers are always vertex set. The naming convention is misleading. Okay? So let us, oh no, this might be, just a second. Yep, I knew that was going to happen. Just a second. All right, so all of that scratch work gone. I am still pushing the button. It is not going. I guess that's as much as we've saved. All right, so we'll just get rid of the other stuff we had. No, not A. Apparently that highlighting did not want to go away. We're going to leave that highlighting because I can't get rid of it. All right. So this guy was A, this guy was B, D, and this one was F. Right. And our previous edge cover, oh no, I now forgot my previous edge cover. So N edge cover was B, D, G, K, I, F, and E. There was no F, I, and E. All right, so now we're looking for the minimal edge cover. Let's start at B again. In this case, when we start at B, go to the left with E. We'll cross off the ones we don't want to use, same as before. But now when we're down here, this is the part where we had issues before where we had we picked too many vertices. Do we need to choose I this time? Do not. So we're going to cross off I, but we do need to go ahead and choose vertex J. Okay? Now, once we've chosen vertex J to be in our edge cover, so our set of vertices where one of the endpoints of every edge in the graph is inside of that set, do we need to choose or select K to go into that edge cover? Turns out we don't. I'm going to go ahead and cross off K. Well, now we jump up into this scenario, and we need to figure out what we need to do. We're told that supposedly J, H, we should be able to select H. Now, at this stage, we're going to make a correction. Okay? We're not going to need to worry about either D or G. I'm going to cross the two of them off. But then that's a problem because we've got two edges right here that they don't have any of their endpoints touching one of these highlighted vertices. So what I'm going to do is I'm actually going to get rid of this guy and say, hey, we shouldn't have crossed off vertex C. That was too soon. Let's go ahead and highlight vertex C. Yeah, we put straight lamps, or we selected vertices on either side of this edge, but it still allows us to have only 5 vertices to put up. Double covered here, but it works out better for the rest of the graph. Okay? So edge covers are not unique. There's tons and tons of different edge covers, and even if you're looking at minimal edge covers, so in our case, we just found a minimal edge cover. There's not always just one smallest way of getting that edge cover. So in different edge covers, you'll use different vertices of your graph. The big thing that is, in order to get an edge cover, is you have some collection of vertices from your graph, and how you know you actually have sufficiently many vertices is every single edge in the graph must have at least one of its endpoints in your edge cover. And this is why it's nice to highlight the vertices that you're selecting in the actual graph, because you're then able to check every single one of your edges and make sure that every single one of the edges has at least one endpoint highlighted. So here, JK, you had to have at least one endpoint highlighted. In our last edge cover, we ended up having both of them highlighted. Did we have both of them highlighted? We did not, but we had K highlighted and not J highlighted. That was just a different edge cover. Oh, did we have J? Did I write that down wrong, the last one? All right. So kind of makes sense, a little bit makes sense. Watch out, edge covers are not sets of edges. They are sets of vertices that interact with edges in a specific way. Oh, excellent. So that means this is the typo. So let me change that for us. All right. So in terms of the thing that is related to an edge cover, and let me make this back to our normal size. So our normal size, again, so the next thing that we're going to look at is something called an independent set of vertices. In terms of an independent set of vertices, what we're looking at is, again, a set of vertices, but this time it's where you don't have any edge that connects any of the two vertices in a set. In other words, it's a set that is dealing with vertices that are not any of them adjacent vertices. Okay? So then when we deal with this guy, I'm on purpose in our example here going to be looking at the exact same graph that we just played with, and the reason for that is to illustrate or highlight the interplay between these two sets of vertices. Okay? So independent set, we want vertices that are not adjacent vertices, or no pair of vertices in that set are adjacent. So here, if we want to look for an independent set, here's what we've got. So I am going to claim that if we just want to find an independent set of vertices in this particular graph, actually, let me be smart about this. Let's actually keep the definition at the top. There we go. So what do you guys think? Anybody have a guess for an independent set? Well, actually, let me rephrase that. Suppose I pick on these two vertices, A and G. Is A and G an independent set? Yeah. So it turns out independent sets are smaller. So where we looked at edge covers before and they were, you could just throw in all the vertices from your graph and it'd be a perfectly fine edge cover, but you were looking really for the minimal edge cover because that was more useful. In terms of independent sets, it's the opposite. Here you're actually going to be fewer vertices the better, because then you don't have any edges between any of those vertices. This is another way of thinking about this is you're pulling a subgraph from your graph where there are no edges at all involved in your subgraph. And that's not by design, that's because you couldn't actually pull in any of the edges based on the vertices you picked or you chose. Now, we had an edge cover last time, and let me go ahead and highlight the edge cover we had. We had what? We had, make sure I grab the right one, E, E, A, C. All right, edge cover from before. Now, suppose you look at this set. A, D, F, G, I, and K. Anybody spot where I grabbed those vertices from? So these are, yeah, so these are the vertices. They're all the vertices in the vertex set, but we threw out the vertices from the edge cover. Okay? So this is literally, if you're thinking in terms of sets, you can think of it as the complement of the edge cover, or you could think of it as the vertex set subtract the edge cover with set subtraction. The highlighted ones in yellow were the ones that were supposed to be the edge cover, as long as I didn't copy anything down wrong. And the ones that we wrote, the A, D, F, G, I, and K, not the minimal edge cover. So I went ahead and grabbed the minimal edge cover, not the original edge cover we found that was not minimal. So if we look at these guys, what do you guys think? These ones that were all of the vertices not in the edge cover from previous, the minimal edge cover from previously, do they look like they would form an independent set? What do you guys think? Independent or not independent? Yeah. So it turns out here's the interplay between independent sets and edge covers, and it turns out sometimes it is way easier to find the independent set, sometimes it's way easier to find the edge cover, sometimes it depends on the graph, sometimes it just depends on how your brain thinks, okay? It turns out that every edge cover, the complement of the edge cover or the vertices that are not in the edge cover are always going to form an independent set, okay? And it turns out that if you look at the minimal edge cover, the vertices that are not in that minimal edge cover will form a maximal independent set, or if you will, the maximum independent set. Now, just like with edge covers, there's lots of different ones. Independent sets, there's lots of different independent sets. And as a couple of you noticed, there's an independent set where you take these highlighted guys and just get rid of either B or C. That's also an independent set. And that's totally fine to think about it that way too. That is legitimately another option. But the interplay here between independent sets and edge covers is they come in pairs. Part of your vertices from your vertex set form an edge cover. The other part form an independent set. Now, you actually have to figure out what that split is. So let me actually write down that relationship, since we've talked about it several times. So this is independent sets and edge covers. So let G be some graph. And let's suppose I, which is some subset of your vertex set, is an independent set of vertices. It turns out that set I is an independent set if and only if, or exactly when, the whole vertex set subtract out, or set subtract your independent set, forms an edge cover. That's exactly what we said before. And to put the comment that we talked about before, if your independent set is a maximum independent set, this occurs only when those other vertices form a minimal edge cover. And that's why I mentioned knowing that interplay is really nice, because again, sometimes it's easier to find one versus the other, especially when you're talking about maximal independent sets or minimal edge covers. It's normally easier to find one versus the other. Again, depends on your graph, depends on how you think about things. And then once you have one of them, you automatically have the other one because you just delete out all the vertices you used for the one to get all the vertices for the other guy. Okay. Questions make sense? Feeling a little bit okay? All right, seeing no questions, I'm going to assume that you guys are kind of okay so far. At least could follow it along if somebody else does it. Oof, just barely got that in. All right, so the last thing that we're going to talk about in section 1.1 is something dealing with is definition of a vertex basis, and then we'll look at an example with it. Okay? I see your comment. I'm not sure what you're asking. Are you talking about this symbol right here? And if yes. So set subtraction is not integer subtraction, and formally it actually needs to have it's actually a slash at an angle, although you see tons and tons of people write it just with the normal subtraction symbol that's horizontal. Set subtraction literally says you remove all of the elements from the set I from set V. So V is all vertices. You can literally describe this as take all of your vertices and remove all of the vertices that were in your independent set. So set subtraction is essentially kicking people out of the set, if that helps. All right, so vertex basis. Vertex basis is applicable in a directed graph, so in a digraph. And what it is, the basis part of it, and remember back to linear algebra, basis is what? It was a set of, and in linear algebra you always called them vectors as sort of the standard buzzword. It was the smallest number of vectors where you could build everybody else, all of your other vectors from. Well, this is going to be similar to that, but different because we're dealing with graphs. A vertex basis is going to be the smallest set of vertices. It's not unique, you could have several different ones, but it's the smallest set of vertices in your directed graph that is the start of a path where that path, or any path starting from that set of vertices, can then go out and reach any of the other vertices in the graph. Now, remember in directed graphs, when you go on paths, you have to follow the direction of the edge. You have to follow these little arrow symbols. So let us look at an example. Okay? So first thing is some notes to the side. So recall, in terms of a path in a directed graph, I have to make sure all of the arrows are going in the same direction, so you'd follow it this way. You can't go backwards along the arrows. And this here does not specify the length of the path, so this tells you the path can be as long as humanly possible. Okay? So you're just trying to find the smallest set of vertices. We're starting there. You can go and follow all of your edges and get everywhere else in the graph. Sometimes there's exactly one vertex that's your basis. That's awesome. But most of the time you have a couple of vertices that form your basis. Now, this example that I've got for us, the graph is already given right down there. It kind of looks like an extended bow tie with extra stuff. I'm going to go ahead and call this graph right here, this directed graph, D for digraph. I'm actually going to throw this to you guys. Okay? So let me go ahead and share this for you guys. This should share on the second screen. So some of you already found this when you first came in today, but I'm going to give you a little bit of time to see if you can figure out what might be happening going on here. See if you can find a basis. So what I did here was in the selections, these are all of the vertices, A through G, in the actual graph itself. Select as many as you think need to go in the basis. Okay? Technically speaking, you could actually select all of them and it would work, but it wouldn't form a basis because it wouldn't be the smallest set. So you want to find as small as possible. This particular example got pulled actually, so while you guys are looking at, I'll tell you where this example got pulled from. It actually got pulled from a psychology study, and the vertices represented people. They threw these people into a group, and the people were supposed to convince other people of some position. And the arrows indicated who was able to influence somebody else. So for example, here on this directed edge from B to A, this would tell you that B was able to influence A to change their opinion to now have whatever the opinion was that B was trying to push through the group of people. So a basis of this digraph would be the people that actually were able to influence everybody else. So that would be a contextual thing. Yes, so a basis is actually not unique, or it's rarely unique. In this case, there's actually 3 different bases you can pick. Please don't actually choose them all. Please just pick one of them for your selection. And I'll give you guys a little bit more time, and then we'll go over how you sort of strategically would find all of your bases. This one being a relatively straightforward example. All right, it looks like the answers have mostly stabilized. So let me share back the work. And this is what I was doing while I hid that picture from you guys for a little bit. So let me go through a strategy in terms of how you can actually find your bases. Okay? So one of the things you can do, as long as it's a relatively small directed graph, or at least it's not larger than what you're willing to do this strategy. Okay? So what you can do is you can actually look to see, all right, well, if we started at vertex A, where are all of the other vertices that we could reach by way of a directed path of any length? So for example, if you start at A, where's another vertex you could reach? Anybody have a guess? Yep, at A, you can totally go to C. You can also go to D. You're not going to be able to cross this directed edge because it goes the wrong direction. You're also not going to be able to go up to B. So A will be able to reach both C and D. Now, what about for vertex B up here? Where could you reach in vertex B? Yep, you can reach everybody on the left-hand side of the graph except coming back to yourself. So this would be A, C, or D. And if you started at vertex C, who could you reach? Yeah, you actually could only reach D. Once you get to D, you can't go anywhere else. Now, what about vertex D? In terms of this psychology context, could vertex D influence anybody? In other words, can you leave vertex D here? Unfortunately, no. So this one here, I'm going to go ahead and just say not applicable, or yes, I love several of the things that you guys sent in, also that way. All right, so now if we go to the other side of the graph, if we go to the right-hand side of the graph, suppose we went and we looked at vertex E, so this guy right here. Where could you reach if you start at vertex E? What vertices could you get to? Ooh, lots, yes. So you could get to D, you could get to G. Now, once you get to D, you can't go anywhere else on this side, so you can't ever reach A, B, or C. We got to G. Could we actually get up to F? Yes, as several of you guys said. How could we get up to F? Anybody have a guess? Yeah, so remember the path could be any length. So we go E to G and then up to F. And actually this one, there's one we forgot that several of you didn't. You can actually keep continuing and get back to yourself. We could actually get back to E. In terms of a psychology problem, influencing yourself, probably not very effective. Okay. Now, what about for F? Any guesses what other vertices we could reach if we started at F? We could get to E, we could get to G, we could get to D. Yep, that's the same. Can we get back to F? And yet, we could actually get back to F as well by going all the way around right here, those three. And last one, at G, who could we reach if we started at G? Same four as the last ones. So D, E, F, and G to put it alphabetically. Now, if you want to find your vertex basis, what do? You want to find where you can actually start to reach as many of the vertices as possible. Can we start at any one vertex and reach all of the other vertices? And the answer to that one is a big fat no. So you're going to have at least 2 vertices in this vertex basis. Now, if we look over here on the left-hand side where you have A, B, C, and D, you want to pick as few vertices as possible to start from. Could we actually pick one vertex that could get us to reach all 4 of these vertices, this A, B, C, D? Yeah. So in your vertex basis, if you start at B, you can totally get to A, C, or D, and starting at B is perfectly fine. We're going to go ahead and pick B. And that guy then takes care of, trying to put a dashed line. That's a terrible dashed line. That takes care of that side. Now, when we look over at this other side, then we need to pick a vertex that allows us to start at that vertex and reach anybody over here. We would prefer one vertex if possible, but if we need to do more than one vertex, we will. So is there a vertex that works where we can get to E, F, or G? Yeah, and it turns out there's many possibilities. Maybe you picked, who was the first one? The first one up there with a single letter gave me E. So this one here, no, they didn't. This F. You can have E, F, or G. Any of those guys would work, which means we actually have 3 different bases for this particular digraph. Okay? But that's the crash course in the selection of various things that you can do with vertices. These last things, other than the matching we did at the beginning of class, the rest of the things have all been dealing with different sets of vertices. Okay? Questions on any of this section 1.1 stuff? Hopefully it makes a little bit more sense. All right, well, seeing no questions, I think you might be missing a word with that question. The definition just has you go out. So if you have some sort of cycle in your graph, you're not going to be able to avoid that anyway. Oh, I get what you're saying. Okay. Anyway, lost my train of thought. So sorry about that, guys. So for the last couple of minutes of class, I'm going to give you a heads up in terms of the next section that we're going to cover. And the next section that we're going to cover is going to deal with isomorphic graphs. So isomorphic graphs are when you have 2 graphs and roughly speaking, they're the same graph, they were just drawn differently. Now it's way more than that. Okay, so if you actually did have the exact same underlying graph with the exact same vertex set and the exact same edge set, and you just physically drew it on the page differently, that's just considered equals. Although if you didn't label the vertices or the edges, you'd still push it into the isomorphic category. Isomorphic is what happens if the labels on your vertices were different. So it wasn't immediately obvious that you had what looks like the same graph, just maybe drawn differently. In other words, we want to know if the underlying structure is the same. There's two definitions that we need, and then everything else in this section is going to be a strategy of determining, hey, are these two graphs really have the same structure or not? The first thing is something called an isomorphism. An isomorphism is a function, and it is actually the mechanics that tell you which part of your graph is the same as which part of your second graph. Okay? So here's the specifics. It's a one-to-one correspondence between the vertices of the graph G1 and the second graph G2, and I was super lazy in the names of the graphs, G for graph, 1 and 2 for first graph and second graph. Okay? For every pair of vertices in G1 that form an edge, feel free to think of this as pick an edge from G1. When those two vertices are mapped to a pair of vertices in the second graph, also going to have an edge in the second graph. In other words, this is a one-to-one correspondence, and here's the buzzwords, that preserves edges or preserves that relationship of edges. Now, how it's used in context if you actually have the graphs in front of you, you would say that if you have two graphs, they are considered isomorphic exactly when, or if and only if, or the condition of when they're isomorphic is you've got that function that's called an isomorphism that's going on behind the scenes. Okay? So all of the heavy lifting is done by this thing called an isomorphism. Isomorphic is the result that you get. The two graphs would be isomorphic if they have the same structure. Okay? So one way to think about isomorphic graphs, sort of the layman's way of thinking about isomorphic graphs, would be, hey, the pictures of the two graphs will look the same if I move the vertices around and if I maybe have to relabel the vertices. So like if one graph, maybe G1, had all of its labels A, B, C, some alphabet labels, and G2 maybe all the labels were letters, not letters, numbers, 1, 2, 3, etc. Maybe you'd have to cross off the 1 and this one and change it to a B, and then they'd be isomorphic, that sort of idea. Okay? Now, practically speaking, there's some results that happen when you have two graphs that are isomorphic. So remember, isomorphic is same structure, so automatically the first thing that you're going to get if you have two isomorphic graphs is the two graphs have to have the same number of vertices. Let me actually write that out in words. Same number of vertices. If they don't have the same number of vertices, you can't have a one-to-one relation. So the question is, can functions applied to graphs add or remove edges or vertices? An isomorphism cannot. However, there are other functions that we have, and one of them is called a contraction, and we'll see that. We're going to look at that when we look at chromatic polynomials in Chapter 2. That's something that when the function actually changes the graph, it will delete an edge or add an edge or merge two vertices together. It's called something different when you do those three different things. But yes, functions actually can do that. Isomorphisms, though, cannot. In this case, this is an isomorphism. You can think of it as a relabeling as opposed to anything else. Also turns out you automatically have to have the same number of edges. And any other property you can ever think of with respect to graphs has to be the same between the two of them because they're literally the same graph but with different labels. When I say literally the same, not really. They're technically called isomorphic because there's a little bit more going on, but they're, roughly speaking, the same graph with just different labels. Okay? So here are the first things that you would check. You check to see that do they have the same number of vertices, do they have the same number of edges. The other thing that you double check is if they are isomorphic, every single vertex in G1 that gets mapped to a vertex in G2, it'll be mapped to a vertex that has the same degree. Okay? So the degree on your vertices will not change when you run it through this function. Okay? And I'm getting too lazy now to check all the properties. So they must have all the same properties. And there's lots of different things that you can check. So I'm about to remind us of something that's logical. Okay? So in a logical statement, an if-then logical statement, you have something like if P implies then Q, and technically speaking, you should not have the if-then if you have the arrow, or you shouldn't have the arrow if you have the if-then, but I wanted to highlight it here. Notice what we're actually going to be doing here in terms of checking. We're actually going to check to see if all of this stuff is true. So our strategy is to check these properties. Okay? So what we're going to look at is if we don't have one of those properties, our conclusion then is the two graphs are not isomorphic. In other words, we're going to be applying, logically speaking, the contrapositive. Okay? Please note, if you actually get all the vertices the same, all of the edges are the same, all of the degrees between the two vertices are the same, and then whatever properties you've checked, so all the properties that you check are the same, that doesn't guarantee the two graphs are isomorphic. It just means if they're not isomorphic, you haven't found the property where they differ. Okay? So once you've come to the conclusion that you think the two graphs are isomorphic, let me write this down, and this will be the last thing we write down today. So if we hypothesize, we're going to stop there, hypothesize that the two graphs are isomorphic. To confirm or to verify, you have to actually build an isomorphism. Now, notice I didn't say the isomorphism. I said an isomorphism. Just like with the stuff that we talked about earlier today, there's not, or there's rarely, one function that maps the vertices from graph 1 to graph 2. You typically have multiple options for isomorphisms that would work if your two graphs are isomorphic. Now, if your two graphs are not isomorphic, there's some property that's not the same among the two graphs, and you'll be able to find it in this list of things. Okay? But that's the idea behind isomorphic graphs. Next time, we'll pretty much all of next time just have a bunch of different examples of two graphs, and we're going to check to see, hey, are these graphs isomorphic or not? And we'll have cases where they are, and we'll build out the function that's the isomorphism, and we'll have cases where they're not, and we'll have to check, all right, what fails? Maybe some of them are really straightforward and they have a different number of vertices. That's an easy check. Maybe there'll be some that actually you have to dig around a little bit more to find what doesn't work. Okay? But I'll go through the major strategies for you guys, and we'll do that. That typically takes about a day and a half, so we'll do that next time and then probably into Friday as well. Okay? But that is it for today. I don't have anything else for us for today. I'll stick around a little bit if any of you've got questions, but that's it.